So, for example, one of the things that you might have done was test the hypothesis that the mean weight of male Temple students is 160 pounds. That's a null hypothesis. And you collected the sample and you weighed everybody and you figured out their average. And you constructed the so-called Z-score. You took that sample mean, you subtracted off the mean under the null, and divided by the variance, which for some reason you knew. So you had x bar minus mu sub 0, mu being the null, and the mean under the null, divided by sigma. And you knew that that random variable was normal 0, 1. And you wanted to reject the true null that Temple students weigh, male students weigh 160 pounds on average, only 5% of the time. Take 10%, so you're 5% in each tail. And you looked up the z-score that cuts off 5% in each tail, and it's 1.96. So if the null hypothesis is true, you've used a method that rejects the null incorrectly a total of 10% of the time. But suppose that the mean weight of Temple students is not 160 pounds, it's something different. Well, when you constructed a z-score which was x bar minus mu 0 over sigma divided by the square root of n. That was the z that you constructed, right? Under the null hypothesis, z is distributed as normal 0, 1. But suppose mu 0 is wrong. Suppose mu 0 is wrong. Does z have a mean of 0? No. Z will still be normal, but it's shifted over a little bit. So we have a null hypothesis that the mean weight of Temple students, male students, is 160 pounds. Against the alternate hypothesis that the mean weight of Temple students is not 160 pounds. We collect a sample and we construct a test statistic that we'll call z, and we'll put a little subscript n on it to tell us how big the sample was that we used. And we say that z is equal to x bar minus mu under the null over sigma divided by the square root of n. You guys know all this, by the way. You should know all this. It should be ancient history for you. And we know that under the null, this z is normal with a mean of 0 and a variance of 1. Suppose the truth is that the mean is 145. We figured out how to solve the obesity problem in America. So the z that we calculated is distributed as a normal. It still has a variance of 1 because I told you we knew sigma. Being a little unrealistic here, but somebody came and whispered it because we knew sigma. So it's still normal, but when the true mean is 145, and we believed that it was 160, what's the mean of z? Minus 15, right? 145 minus 160 minus. So what's the implication for the way we conduct our tested hypothesis? Well, that's what we thought the distribution would be. And we could find the weights that cut off 10 to 5% in each tail. But the distribution really turned out to be 145. And this was x bar star lower and x bar star upper. So if this is the truth, the probability of finding a test statistic down here is much bigger than 5%, and of seeing a big one is really small. But because of the shape of things, this swamps anything that we gave up in the upper half. So if you wanted, I suppose we could be really racy and we could say that under the null, our normal is centrally distributed. It's distributed at 0. And under the alternate, there's a distribution that's centered somewhere else. Well, the same thing works with chi-square and f. Under the alternate, our chi-square test statistic is non-central. It puts a lot more probability in the tail. Out there past our critical value. Same thing with an f. Under the null, your test statistic is a central f distribution. Under the alternate, it's non-central. But the f gets pretty tricky. Because remember, the f is the ratio of 2 chi-squares. So the f can have 2 non-centrality parameters. Conventionally, the way things are done, when we believe that if the null is not correct, that for sure we know the alternate, and the alternate is correct, then the f that we're using is a singly non-central f. But sometimes neither the null nor the alternate are correct, in which case our f statistic is doubly non-central. When we come to that, I'll point it out. Oh, we don't want to. We're hoping that, suppose that my null hypothesis is that the mean weight of Temple male students is 160 pounds. And the truth is that it's 159. Do you think that on the basis of my sample of 100 students, I'm going to be able to see that? No. Because the truth is so close to my null hypothesis that moving the density over a little bit doesn't change the probability in the tail much at all. So my test doesn't have much power. But if the truth is 145, probably with my sample of a size 100, I'm very likely to see that 160 was wrong. So I don't want to correct the non-centrality. Heretofore, in your tests of hypothesis, your tests of hypothesis were always based on using minimum variance unbiased estimators, because you decided that the penalty function that interests you, well, you didn't decide it, people who were teaching you decided for you, that the loss function that concerned you was squared error loss in the class of unbiased estimators. I don't know if you were told that, but that's the way you built all your tests in the past. You built your test statistics so that you were minimizing in class of unbiased estimators squared error loss. But suppose, a little parable by way of introducing the next idea. There's a little fable or story about the constable finds Clancy crawling around under the streetlight across the street from the Irish pub. And the constable says, Clancy, why are you crawling around here on the floor, on the ground? Clancy says, I'm looking for my keys. I dropped them. And Clancy and the constable says, well, Clancy, did you drop them? Where do you think you dropped them? And I said, well, I think I lost them when I was coming out of the pub. And so the constable says, well, why are you looking here? And Clancy says, well, the light's better over here. Well, sometimes we do the same sort of thing in statistics. Sometimes we can come up with estimators other than least squares, which have smaller variance. They're biased, but they have smaller variance. And as long as we know the direction of the bias and can make a suitable translation, then we might choose to use an estimator which, in that sense, has smaller mean square error. If we're using a test statistic based on that criteria rather than just minimum variance, we have to read our critical values not out of a central F or central chi-square. We read them out of a non-central F or chi-square. And there's another criteria that we might use for testing hypotheses, which is based on minimizing the risk, where risk has a very special definition. We might choose an estimator that minimizes risk rather than mean square error or variance, in which case we have a different non-central F altogether. So when we're using these other criteria besides the traditional least squares test statistic, we're using mean square error or risk, under the null, the test statistic has this non-central F distribution. And so we're reading the critical values out of different tables that you learned how to use in your basic statistics class. So we're going to come to all this much later.